Hello, my name is Dave Benham, and today I want to talk about the Instruo Neoni oscillator available on VCV Rack. And there's been a lot of discussion about how the FM works on the Neoni, on the VCV community, and some debate. The interesting thing about the Neoni is it does linear FM, and it's true frequency modulation, not phase modulation. Most digital oscillators do phase modulation. But not only is it linear frequency modulation, but it's also through zero. So you can supposed to be able to use it melodically and not have to worry about it going out of tune as you apply the FM. Before I talk about, before we even go, if you haven't watched Jason's video from Instruo where he introduces the Neoni, please watch that. It's a long video, but it's really worthwhile. It not only does it do a great job of showing all the amazing things that the Neoni can do, from a hardware perspective anyway, he also does a great job of explaining how the FM works. But even after watching that, I still was confused about a couple things. And so I did a bunch of experiments to try to better understand exactly how this through zero FM was working. And I want to share some discoveries. I think they'll be surprising. They were really surprising to me, and I think they're going to be surprising to a lot of other people. But before I get to the Neoni, I think I want to start just with the fundamental, starting with VCV Rack 2. They introduced the ability to do linear FM frequency modulation. Before it was always frequency modulation, but it was just exponential, and now they got the button for linear. But it's not through zero. So I think that's the typical, especially in the analog world. Linear FM most often was not through zero. So in order to investigate how it works, rather than apply an audio rate oscillator to the FM, which you typically do, I want to apply constant voltage so that we can actually look at, we can investigate how, as the signal coming into the FM input, as the voltage varies, how does it affect the frequency of the oscillator, of the carrier wave. So I've got the fundamental VCO outputting a saw wave. It's tuned to C4. We've got zero voltage going into the volt per octave, and it's at its default frequency. So it's a C4 like you'd expect. And then going into the FM, I've got volt knobs. It's also at zero. It's at the bipolar mode. So at 12 o'clock, it's producing 0 volts. Going into the FM with 100% attenuation. So we can raise the voltage, and so it's going to increase the voltage of increase the frequency of the oscillator, but we expect that. We go down below 0, and it's getting slower and slower and slower, lower frequency, and then eventually it stalls. And that's around -1 volt. So to make things easy, rather than use knobs, I've got a bunch of pre-calibrated constant voltages here from the fixed voltage source from NIST. So if we're at 0 volts, of course, we've got the C4 that the fundamental's tuned to. If we go up 1 volt, it goes up 1 octave. And if we go up, so if this is linear, right, we want to, in order to go up by another octave, if it's linear, we need to double the frequency. So if it went 1 up, if we had added 1 volt to go up 1 octave, then to get to the next octave, we should have to add 2 additional volts. So 1 volt plus 2 volts would be 3 volts. And there indeed we have our C6. We're up to the next octave. So to get to the next one, we would have to add, we just added 2 volts, so now we need to add 4 volts to double the frequency yet again. 3 plus 4 is 7. We're up yet another octave, and we can go on from there. And if we go down to 0, right, the base frequency, if we subtract 1 volt, it should go down to 0 hertz, and we indeed stall. And we can go as low as we want. It's the oscillator just can't go below 0 hertz, right? If we makes all perfect sense. And then if we change the base frequency of the fundamental, let's add 1 volt. So let's make the fundamental start from a C5, and we're adding 0 volts to the FM, so it's playing a C5. If we add 1 volt, it doesn't go up an octave, right? So let's add 2 volts. Okay, that makes sense. So it's linear FM, and the hertz per volt is constant. So if we to go up 1 octave from C5 to C6, we have to add 2 volts. Then we should have to double that to get to go up the next octave. So 2 volts plus 4 volts will be 6. And yep, we went up the next octave. And then to go yet again, we need 1 more octave. We need to go double the 4 volts is 8 volts. So add 8 volts to 6 to 14. And we're up to that octave, the next octave. So going in reverse, starting at 0, we go down -1, it's not going to stall, but if we go down -2, it stalls. Everything makes perfect sense. We kind of have an understanding how the fundamental works. So let's now bring in the Neoni. And it's an entirely different beast. We'll go to saw wave as well. And it if we go to we want the through zero, right? We don't care about that. That's the interesting thing coming in. So not LFO, I'm sorry. We'll switch this down to through zero, and right away we're at 0 volts coming in to the FM input. Even if we bring this up, right? So we got 0 volts coming from, I'm sorry, let's bring these voltage sources down in here. If we got 0 volts coming in, it stalls already, and that's right away we're very different than the VCV VCO. Let's bring this over to knobs. We're at 0 volts. We raise it. Okay, we're modulating the frequency as we increase the FM input voltage. That makes sense. If we go down negative, okay, we can see that it's through 0. It gets past the 0 and it's kind of reflecting back. So that makes sense. And Jason talks all about this. One other thing, and Jason mentions this, we're starting out with a saw wave in the positive side. As we get to the negative region, it becomes a ramp, so it inverts the waveform, positive versus negative. And it's not exactly 0 where even though the stall point 0, the inversion is not exactly 0, and it turns out it's -0.2. If we give it -0.2, it's a saw wave, and just let's add 1/10 of 1 millivolt, and it switches to a ramp wave. It's we can see it better if we go there. There we go. -2.001 volts. It's a ramp wave. Go back to 2, and it's back to a -0.2. I'm sorry. It goes back to a saw wave. But now we want to look at it's supposed to be linear, right? If we are starting at 0, what does it take to get to the fundamental voltage? Remember, we started at C4. So what is it going to take to get back to C4? So turn on the through zero, and if it turns out, I already know the answer. If I go to 1.08 volts, we're at our Z4. It's as close as I could get. It's not the amount that you could tune it. It's not infinitely adjustable. Double it, 2.15 more or less, and we're at our C5. But now to get to the next octave, we added 1.08. We need to add double that, so we need to go up to 4.29, 4.3 or 4.29 is what it turns out to be, and we got our octave that way. And I'm just going on the positive end, but because this is through zero, right? So if we're zero stalled, 1.08 is our base voltage, our base C4 that the Neoni is tuned to, and the negative should be the same thing, but the ramp wave. So we got 2.15. Let's make this so we can see it a little better. 2.15 for one octave up, minus 2.15 would also be one octave up, but the ramp wave, and it goes on from there. So then, okay, what happens if we tune the Neoni to a different frequency? So right now it's at, it's not getting any input, so it's C4. Let's add 1 volt to the Neoni. Let's go up here to do it. And we're at our C5, more or less. We can, if we want to fine tune it, we can. I'm sorry, that's what here we go. So we got the Neoni tuned to C5. So now what's it going to take? If you go to through zero, and it's 0 volts, it's stalled again. What's it going to take to go up to the C5? Well, let's try the 1.08. Well, there it is. So, and now if the 2.1 minus 108 also is that same octave, the same 2.15 minus 2.15. So what's happening is the number of hertz per volt is scaled relative to what the base tuning of the Neoni is. Very different than the VCV Fundamental VCO. Also with the same tuning though, it's still at minus 0.2 volts. We've got a saw wave. If we add 1/10 of a millivolt, it still inverts at minus 0.2 volts, or just beyond minus 0.2 volts. So, what does that mean? We can come up with a formula. Let me turn this off here for a minute. We can come up with a formula, actually, that can predict what the frequency is going to be. For through zero, the frequency, the output frequency, is going to be equal to the absolute value of the base frequency that the Instruo Neoni is tuned to, divided by 1.08, times the voltage coming into the FM input. Let's see what happens with traditional. So I'm assuming it's just going to be linear FM, but no compensation for through zero, so that I would expect it to stall once we get to negative voltages. So we go to traditional mode. Let me turn this back up, and I will, let's go to the knobs again, just to investigate this real quick. We're at 0, and that's, I'm sorry, let's put this back down to C4. So that's our starting point. And then we can, as we increase the voltage on the FM input, It goes up as we expect, and we're not stalled at 0 volts. Okay, that's good. And it's looking kind of like, wait a minute. I don't know if you caught that. We started out at the saw wave, and here we are at minus 0.2 again. It inverts. Now that's a surprise, because this is traditional, right? I was expecting this not to have through zero compensation. In fact, we can prove that it's the exact same minus 0.2. At minus 0.2, it's a saw wave. Add 1/10 of 1 millivolt, and it inverts to a ramp wave. Okay, that's a surprise. Jason never says exactly what the traditional is. I just assume, and I've never seen it in writing, I just assumed by traditional that it didn't have any through zero. Well, let's keep on going negative. It's slowing down, and eventually it stalls. And if we look at the voltage, it's minus 2.09, or round that up to minus 2.1. On it down, whatever. But now let's keep on going. Wait a minute. We're increasing the frequency again. So clearly, even though this is quote traditional, there's through zero compensation. It's just not centered around zero, right? It's offset by minus 2.1 volts. And I've already got, we can look at this more precisely. I've got some fixed voltages already set up. So we start at zero. We start at zero, and we're at our C4. And we go to minus 2.1, and we're at our stall point. 0 is the base frequency, and minus 2.1 is the stall point. Then I would expect to add, if this is linear, then if I add 2.1, that should take me to 1 octave up, and indeed it does. Minus 2.1 to get it down an octave, I should go to minus 4.2. I'm sorry. 0 minus 2.1 is the stall point. Add 2.1 to 0. It's at the base. It's at the base frequency of C4. 0 minus 2.1 minus 4.2. We're at the base frequency. Now to go up, we go for 0 an additional 2.1. We're up 1 octave. 4 minus 4.2 minus an additional 2.1. Minus 6.3. That same octave. Now to go from 2.1 up to 1 octave up again, we got to double that amount, so it ends up being 6.3. We drop an octave, and then minus 6.3, it's the 4 point whatever it is we had, minus 10.5. We're at the same octave again. That fascinates me. I was totally not expecting that result. And we can create a formula for this as well. So for on the Neoni, for the quote traditional, for the traditional FM, the frequency is going to be equal to the absolute value of the base frequency divided by 2.1 times the voltage, the current voltage at the FM input, plus 2.1 quantity, and then the absolute value. And I was thinking, why on earth was it done that way? It didn't make any sense. And then all of a sudden it dawned on me, oh, so rather than have two different circuits for traditional and through zero, he just changed the coefficients so that, you know, what's the difference in the sound? I'm sorry. Let me go to the. Well, let's use the VCO here. We'll use the fundamental VCO as a modulator. So let's look at the difference between traditional and through zero. I mean, if you watch the video, you're going to get this already, right? So no way it's a waste of time. But let's use the VCO as a modulator, as it normally would be, into the FM input. And we turn up the volume, and that sounds pretty nasty. And we adjust the modulating frequency, and all kinds of chaos is happening. And the same is true if we adjust the Neoni. Different type of chaos, but it's still pretty harsh changes. But if we put it in through zero mode, now we've got this wave folding going on, but it's the base frequency is constant. Jason explains this. It's the inverse of what people expect with with frequency modulation, but because of the way it's being done here with a through zero, this is the expected result. And if you change the modulating frequency, it adjusts the pitch. The modulator sets the pitch, and the carrier wave and the Neoni changes the texture. All right. So, I mean, there's clearly a difference in the traditional from the through zero, right? And the end result about sonically what you get. But the reason for why he did the math that he did, I mean, they're both actually doing through zero compensation, but the through zero, quote, the one that's labeled as through zero, is centered around 0 volts. And so typically, right, you're modulating wave is also centered around 0 volts. So it's symmetric on both sides, and that's what negative and positive, that's what lets it be more harmonious. And the quote traditional is offset from 0. Now the negative and the positive are not symmetrical, and that's the source of all the chaos. And if you just look at this for the traditional, if you put in your base frequency, if you put in 0 volts, we want, when it's in traditional mode, if you don't have any input on the FM, then you want it to be the same as if there was no FM taking place, right? So if you put in your base frequency divided by 2.1, but on this other quantity over here, it's the current voltage, 0, plus 2.1 is positive 2.1. So we got 2.1 over here divided by this 2.1. That's 1 times your base frequency. You haven't modified anything. So that's why when you put it in traditional mode, you don't think there's anything going on, but it's actually applying the frequency modulation. And it just so happens that there is no input there, so it's not doing anything. And it's chaotic in traditional mode, harmonious here. So, all right, I've got these formulas. What's the big deal? I mean, it's surprising. Okay. I looked at this some more, and I thought, well, wait a minute. I mean, these have the same basic formula, just changing the coefficients. I ought to be able to modulate the modulator. I ought to be able to change the incoming modulation signal in such a way that I can make this traditional FM sound like the through zero. And all I should have to be able to do is, first off, this coefficient here, 1.08 versus 2.1, that's basically a factor of 2. So for whatever, if my through zero is at frequency A, in order to compensate for my traditional, I need to be 2 times A to compensate for that difference in the voltage, right? 1 divided by 1 is 1. If I got 2 divided by 2, that's also 1. So double the frequency of the Neoni, and then also I need to offset the incoming modulating signal negative 2.1 to compensate for the offset in the way the Neoni is configured. And down below, I've actually implemented that. So here I have got a patch. Actually, let me set this up to bring the audio back in to our switch down here. I was going. Sorry, I want to go from output to input. There we go. In this patch, we have 2 Neoni oscillators on the top. We're going to be in through zero mode. The top traditional Neoni's in through zero, the bottom one's in traditional, and we're going to use a Bogue Audio VCO as a modulator, and we're going to start with a sine wave going into a mixer. That's just adding a sample delay. I'll talk about that in a second. Well, I'll talk about it now. Some of these mixers are, the only point is to add a sample delay because I want all the oscillators and all the signals to be coming at the same time to keep everything in sync as much as possible, to be able to have the waveforms and everything match each other. So I've got this sine wave going in, and then it comes to this second, this first mix. I'm also using it as a attenuator, so I can attenuate FM both Neonis at the same time rather than have to tune each attenuator here separately. I can tune them from here. But then it goes to another mix, and from there it goes to this first Neoni in through zero mode, and it also goes to for the bottom one, it goes from here over to a Bogue Audio offset with a minus 2.1 volt offset and a scale of 1. So that is the 2.1 offset in the formula here that we need to do the compensation. So that's to offset the modulating signal. So the green wave up at the top here is what's being fed into the top Neoni, and the yellow wave is offset minus 2.1. You can see the offset feeding into the traditional mode. For the other part that we have to take into consideration is scaling the Neoni base frequency. So we're controlling both oscillators with this top knob. The volts knob goes directly into the top Neoni in through zero mode into the volt per octave, but it also goes down to the second knobs too at 100% attenuation, and then we add the value of this knob, and that's set at 1 volt. So if we set this top knob to and that goes to the bottom one in volt per octave, so that is our factor of 2. It's 1 volt is 1 octave is doubling the frequency. That takes care of our difference in our coefficient in the divisor, 1 versus 2 basically. So if we have this, if we look at this, I love this new feature of version 2 where you can actually look at the voltages that's at the input or the output at the jack location. Right now that's set at 1.57, so just verify the bottom one should be 2.57, and indeed it is 2.57. Well, same thing at the inputs here, right? 1.57, 2.57. The last thing that's going on is besides the sine wave as our modulator, we're also using the square wave at the same frequency to keep everything in sync. It's syncing up the oscilloscope over here and the oscilloscope that I'll turn on in just a second. And I'm also, actually I don't have it on. Let me put it in there. just to keep everything in sync between the two oscillators to make the comparisons easier. I'll demonstrate that it doesn't impact the sound, but it does help. Just making sure everything's synced up as much as possible. So if I re-enable these things over here, and we've already got a signal, and this is already looking promising, right? Even without hearing the sound, top and bottom look the same. Green is through zero, yellow is traditional. Normally they would not be, they'd be radically different FM, but because of this compensation, and I forgot to mention this, in order for this to work, it needs to be in DC mode, right? If I'm in AC, it's not going to work because that'll get rid of the offset. So I need to be in DC mode, and so that offset, it has to be a symmetric wave around 0 coming in, but offset by minus 2.1, and likewise it's symmetric around 0 for the top one. So that should work for the Neoni. For the through zero, let me put them both at sine wave. Actually, turn up the sound a little bit, and we're in switch position 1. That means we're listening to the through zero, and I can sweep the Neoni bass frequency, and it's having fun with those, effectively folding the wave and giving interesting frequency modulation. Well, the FM is having an interesting effect. And if I switch to the traditional, exactly the same. And instead of me having to move it, let me patch in a oscillator and let that sweep the Neoni. And I'll turn this, I'll attenuate it a little bit. So I can, here we're listening to the traditional, position 2, position 1, through 0. I can go midstream, I'm switching back and forth. They're giving the exact same result. And I can change the bass frequency. I can go down. Changes the pitch, right? The modulator in this form of FM, the modulator sets the pitch. The carrier wave sets the texture. Switching back and forth between through 0 and traditional, and not hearing any difference. Put this in AC mode, and put it on right now a traditional mode with that offset's not active, so it's totally different, right? But put that DC on and they sound the same. We can do different waveforms. Put it on triangle. Let's see. Yep, they're still in sync with each other. It still sounds one and the same. I said that I'll show that the sync really isn't having any effect on the sound, so I'll demonstrate that now. What are we on? We're in through 0 mode. Take away the sync signal. It doesn't affect it. Switch it over to traditional mode. Take away the sync again. Just the same result. But as I without the sync and I twiddle knobs and whatnot, things can get out of sync, and then the comparison is not as valid. We can also change the waveform of the carrier. Let's put it on square wave, and that's kind of cool. We got the square wave modulator with the triangle carrier wave. Results in this interesting folding triangle wave. Anyway, totally unexpected. It kind of validates my measurements and my formulas that I've got here. The fact that I can make the two sound the same. And for me, real educational to help me understand what's going on with this oscillator, and in the process of doing this, help me understand FM just kind of better in general about how the frequency modulation is set up on the various oscillators. So I hope you all, anybody that's watching, hope you found this interesting, and until I make another video, I'll have a good day or good night, whatever it happens to be for you. I'll talk to you later. Bye.